Hi everyone. It's a pleasure to welcome Uri Kol. He's a postdoc at the Center of Mathematical Sciences and Applications downstairs at Harvard, and he'll be presenting on duality and integrability in black hole physics. Really excited to have him. It's a pleasure.
Yeah, thank you so much, Prashant and Aaron, for inviting me. And sorry for the delay with the technology stuff. But anyway, yeah, I'm a postdoc at CMSA. My background is in different topics in energy physics. I work in the past on ADS-CFT, holography, and things like that. And today, so we thought that we'll do a series on several works that, in particular, in collaboration with Alfredo, on duality and integrability in black hole physics. So, the main point is to try to solve to understand black holes. Right, this is what we are here for, and to have something more concrete in mind, we would like to solve something like the two-body problem, but this is very hard. So we've all seen this picture thousands of times, but let me just review it for the sake of clarity. So we break this problem down into different regions of the process: the in-spiral, the merger, and the ring down. And we can use different approximations in each one of these regions. I will focus on the ring down region, in which the two bodies already essentially merged, but they still settle. And in this region, the process is controlled by the quasi-normal modes of the black hole. Or maybe I should also say before that, just some general words. So yeah, we want to find some tools that will help us understand and be able to solve more exactly this kind of problems. Yes, so this ring down phase is controlled, as I mentioned, by the quasi-normal modes. So of the black holes. This is an example. One of the main papers on the subject. And well, these quasi-normal modes also are related to the photon ring that has been discussed here a lot, and the Black Hole Initiative has been leading the effort on this front. And of course, all of you know much better than me about the photon ring, but I just want to say that these quasi-normal modes also are related to this kind of process, so it's important to try to understand and compute them and get as much as analytical and on this calculation, or otherwise some kind of understanding. So how do we compute these quasi-normal modes that control the ring down phase of the process? We need to compute the scattering of a wave from the black hole. This is done using the Tukolsky equation. So Tukolsky studied this problem of the scattering equation of the Kerr metric in '73. So this is the Kerr metric, and he derived the scattering equation. Now it looks complicated, but it could have been much more complicated. And the fact that the scattering equation is separable in this form into separate functions of the four coordinates is kind of a miracle. We don't till today. No one knows why is that so, but it is. And yeah, so it is separable into the radial and angular equations. So the details are not important here. There are different factors that are related to the metric. The few things that are important is that it depends on this parameter S. S is the spin of the perturbation, so it can be a scalar, a vector, or a metric perturbation. It's a quite general formalism. And ideally, we would like to solve this equation, find the eigenvalues, the eigenfunctions and the eigenvalues for the energy. And those would be the quasi-normal modes of the Kerr black hole. I will not talk much about the angular equation in this talk. I will focus mostly on the radial part. And yeah, so that's what we would like to do, but the problem is that it's very hard. Solving the Duality equation is very hard. It is essentially an ordinary differential equation with 4 regular singular points, and which is known as the Owen equation, and there is no closed form solution to this. So that's a challenge. And of course, since the discovery of the Duality equation in 73, there has been a lot of effort, mostly numerical, but on the analytical front, there is not much known. So the question is, can we do better than that? Can we use more than 100 years of knowledge of quantum mechanics, knowledge and experience of quantum mechanics and quantum field theory to do better than that? And a clue is perhaps this article by Robert Dijkgraaf that the title is "The Black Hole is the Atom of the 21st Century," and we know that it's kind of a theme that people have mentioned. So the question that I want to pose is that if black holes are the atom of the 21st century, can we follow the footsteps of quantum mechanics and quantum field theory and try to develop tools, similar tools in gravity? Okay, so yes, so the first, or let me put this way. Some of the milestones in the development of quantum mechanics and quantum field theory is, of course, the discovery of the hydrogen atom, which is an integrable system. It's there is a solution in terms of known functions, and as we all learn in school, this is perhaps the only realistic system that can be solved exactly. So, can we have an analog of this integrable system for black holes or in gravity in general? And if so, what can we do with that? Can we go further to perturb the hydrogen atom and learn about more general systems? Can we have some non-perturbative techniques like in field theory as duality is an example? And I will say a little bit more about what is this, even though it will not be anywhere close to the main subject of the talk, but just to have some general idea in mind. At least my idea is that we can learn from, again, more than 100 years of knowledge of these subjects and try to use this kind of techniques.
Are those two questions connected?
With these two?
Yes.
I will explain how they are connected.
Okay.
It's not exactly the same thing, but yeah. Any more questions? Okay, so this is the plan for the talk. I will start with an interview I will start with a review of the central potential problem in quantum mechanics. So this is the hydrogen atom, but in fact it's a class, it's a family of problems that can be mapped to each other. And it includes also dion scattering, dion and dion scattering. So dion is a particle with an electric and magnetic charge. And this class of problems, they all boil down to the harmonic oscillator. They can be mapped to each other, and they are integrable. So I will review this problem or set of problems, and I will also emphasize the role of duality in this. Yes, or aspects of duality, electromagnetic duality. So that will be a review that will set up the stage for the following discussion. So in this talk, I will so that will be a review, and the new results will be about how can we realize duality, which is similar to electromagnetic duality in general relativity, and that, in my mind, will open the possibilities in the future to use some non-perturbative techniques, as I mentioned before. And that it will also prepare the ground for the next talks by Alfredo about our joint collaborations about integrability in GR. Okay, so that will not be today, but I will review the story in quantum mechanics, and then it will be easier to follow the story in general relativity. Okay, any questions?
Yeah, I want to go back right to the beginning.
Yes.
So the Tucholsky equation is a perturbation equation, right?
Right.
Okay. So even though the original equation is non-linear, you got a
It's
perturbation.
linear. It's linearized perturbation.
It's linearized.
Yeah.
So then why is it so surprising that you can get a separable solution?
Why is
To
it
me,
so surprising?
Yeah, I would have said, yeah, of course it's going to be so.
It's surprising because there aren't enough symmetries to start with.
You have the phi symmetry.
You have the phi symmetry.
So you should get an e to the im phi to be
Yes, but R and theta are still separable.
Sure. Oh, so okay, I didn't see that.
Yes, so, yeah, that's the magic.
Oh, I see. The
R and
theta and R separability.
Yeah, exactly.
Okay, fine.
Exactly.
But the T and the phi is
Yes,
okay, right?
Yes. Yes.
Okay.
So no one really understands why is that. So exactly, there are some clues. There is something which is called the Carter constant. So there is another constant of motion, but it's something that we didn't start with in the Kerr black hole. Kerr is just
Okay.
So it's not completely why it should have been like that.
Good. But it is this magic
Yes.
that reduces it to an ODE in R,
Yes.
right?
Yes. Exactly.
That's the whole point here.
Exactly.
And then solving that
Exactly. It's very
with 4 singularities. Okay.
Right. Exactly. Exactly. Yeah, I'm not going to address this question of why is it separable, but not today at least. But it's something that people around here, including Alfredo and I and Andy Strominger and other people are thinking about. Okay, any more questions? Yeah. So let me start by reviewing the story of the hydrogen atom to remind you of the details of this problem. So the hydrogen atom is a quantum mechanical system. We solve the Schrödinger equation with a central potential, and the wave function is given in this form. We have, of course, the time and the energy dependence, and the spatial dependence is given by this solution. So that's the one-known solution of the hydrogen atom. It is given in terms of the Laguerre polynomials. So those are functions known explicitly. They are polynomials, fine. Yes, and this is the spectrum, the eigen values of the problem in terms of the both radius and that is discrete, of course. Okay, so this is the wave function for the hydrogen atom, the central potential problem. Let me review some group theory of this problem. So in fact, Pauli saw the spectrum of this problem before the Schrödinger equation was known. And that's what so if you see this the paper by Pauli, this is the paper by Pauli, the beginning of 1926, and I think that Schrödinger equation was derived only a little later, the same year, I believe. How did he do that? He did it using group theory of the central potential problem. So here I'm using slightly different notations for the Schrödinger equation, and slight change of variables and maybe the coordinates, but we can bring the Schrödinger equation to this form. Well, here this operator gamma 0 is the Hamiltonian, and this is an eigenvalue problem. So we want to solve for the eigenvalues of this operator, which are the energies. Now it turns out that this Hamiltonian is invariant under a very large set of symmetries. Not only it is invariant under angular momentum, there is also a Laplace-Runge length vector, 3 conserved quantities, under which the Hamiltonian is invariant. Now, I think that Alfredo will talk more about the Kepler problem and the Laplace length vector in his talk, so I don't want to spend too much time on this. I will just say that this set of operators, the Hamiltonian and the 6 conserved charges, span a larger group. So the Hamiltonian is part of a conformal group, SO 2,1, with these 2 operators, and they commute with each other to span an even larger group, SO 4,2. And Pauli used this group theory arguments, essentially. This is a slightly more modern language, but essentially use this argument to fix the eigenvalues of this Hamiltonian operator in terms of quantum numbers of this group, so 2,1. So yes. So once we do that, the spectrum of the hydrogen atom that I wrote before, which today can be just solved explicitly, plug in the equation into mathematics and solve, but it has a group theory origin. And this is the origin of the quantization, this conformal group. So this is the Hamiltonian essentially, and those 2 operators are essentially ladder operators that take us up and down the level of the energy. More precisely, linear combinations of this set of operators are the ladder operators. So this is a group theory understanding of the problem. And maybe let me spend 1 minute about explaining what is integrability, because it was in the title. So integrability is the ability to solve exactly for a problem, and to solve exactly, in order to solve exactly for the problem, we need to have a maximum set of quantities. So, for example, in this problem, we have 6 degrees of freedom on the phase space. The coordinate, spatial coordinates, and the conjugate momentum. And we also have 6 conserved charges. As I mentioned before, 3 angular momentums and 3 components of the LRL vector. So we have this. We have the same numbers of conserved charges as the number of degrees of freedom, and that means that the system is fully constrained and explicitly given in terms of these charges. And this is the property which is called integrability. Okay, so that's just to clarify what's the meaning of this word. Yes, so so again, following the footsteps of the development of quantum mechanics, after people realize the structure of the hydrogen atom, they also perturb around it, right? So if we consider perturbation around the integrable model, so here the Hamiltonian is given by some integrable Hamiltonian plus a correction, we can do a perturbation theory around it and compute the corrections to the spectrum. And yeah, so there are different types of corrections. Let me review the standard ones, which are called the fine structure corrections of the hydrogen atom. So one type of correction is relativistic corrections. And again, the details here are not important. I just want to deliver the message that these corrections can be computed using various methods. Actually, but this is perturbation theory. And using this perturbation theory, we can compute the corrections to the spectrum. This is one type of correction, and we have another type of famous correction, which is due to spin orbit coupling in the Hamiltonian. Yes, so the details are not important to you. It's just that I want to review this concept, mostly for the sake of Alfredo's talk next week. Yeah, so it turns out, as I mentioned at the beginning of the talk, that the hydrogen atom is not alone. It's a part of a family of problems that can be mapped into each other. this problem includes all this set of problems with the central potential. So that includes not only scattering from an electric charge, like in the hydrogen atom, but also including a magnetic charge. But not just that. It turns out that also not just the Schrödinger equation as with the central potential as the integrability property, but also the Klein-Gordon and the Dirac equations are integrable. That was that's a, well, it's less famous, but pretty seminal work of Barut and Borzin, where they showed that, and they also showed the group structure that I mentioned before for all of these problems. And yes, so as you can see here, the equations depend on the parameters, the electric and magnetic charges of the two dions. So this is a problem of scattering of two dions of each other. And we can recover the hydrogen atom by setting the magnetic charge to 0 and focus on the Schrödinger equation. But this is a set of a family of problems that are all integrable and can essentially boil down to the harmonic oscillator. Notice this combination that appears here of the electric and magnetic charges. I will come back to it soon and will explain its origin.
Okay, one question.
Yeah.
So when you consider all these different, like the scalar piece and also the Dirac piece, is there any assumption about how they're coupled at the level of the action? Are they all minimally coupled?
Yeah. I mean, this is a statement about the coupling.
Okay, so it's all minimally coupled.
Yes, in the case of Klein-Gordon, for example.
Okay.
So the Tukhowsky equation will essentially boil down to the Klein-Gordon for a scalar.
Yes.
Yes. So yeah, this is just a few lines about the
question.
Oh yeah.
Alfredo.
Yes.
Yeah, I just comment. Yeah, can you hear me?
Yes, we can hear you.
Yeah, I just had a comment on this slide. Apparently, these integral structures were found around the same time that Duality came up with the separability of the wave equation. So I was wondering if this is somehow a coincidence, or indeed people were looking at these sort of structures during those years. I don't know if you have any input on that.
I couldn't hear correctly, but you are asking if it's a coincidence that it appeared around the same time as Tukhowsky? That's a question?
Yeah.
Yeah, it's an interesting question. I didn't think about it. I don't see. Yeah, I'm not sure that Tukhowsky was aware of this. At least I don't remember that he referred to it, but we can check it later, perhaps.
Yeah. Okay.
I think it's a different. This is more like people that worked on the hydrogen atom, and Tukhowsky was an astrophysicist. So I'm not sure that he was aware of it. But I'm not
Actually, on that point.
Yeah.
So integrability is not the same as separability, right?
Right.
Okay, it can be integrable, but it may not be separable in data.
Yes, even though when it's not separable, it's harder to imagine how you can solve it. But yes.
Okay.
Yes.
No,
And it
integrable
implies
can actually integrate.
separability. Yeah, integrability implies separability.
It does?
Integrability implies separability.
Okay, I guess I didn't know that. Okay.
I didn't know that either.
Yeah, not
So if you can write a Hamilton's principal function in place space, which is given by the right number of conserved quantities, you can essentially separate the wave equation.
Yeah, within the Hamilton-Jacobi formulation, you can start off with the Hamilton-Jacobi function, I think.
Right.
Yeah.
Right. So integrability implies probability.
Yeah, but I don't know if you could actually write it down.
Okay. Yeah.
But it can be separable and not integrable. Yes. And any more questions?
Sure.
Okay. So yeah, so in the same way that the hydrogen atom can be solved, the dion scattering can be solved as well. And I think that Coleman noted that, so this is the central potential, right? But it was noted that the coupling to a magnetic charge, the effect of the coupling to a magnetic charge adds a force which looks like the centrifugal force. So it adds to the centrifugal force. So this coupling equation of two dions can be solved exactly again in terms of known functions that confluent hypergeometric function, which is actually the same as the Lapierre polynomials that I mentioned before. So it really is the same thing. And the spectrum is quantized, and here this quantity, which is usually called in the literature L theta, in terms of the angular momentum, and this quantity mu, which is E times G, so that quantity appears all over the place in this kind of problems of monopole scattering. And this quantity L theta, just as a side comment, is controls the scattering amplitude. This is essentially the data that goes into the scattering amplitude. It's called the phase shift. And this is really kind of a side comment. But when people computed, this is mostly works by Schwinger, computed the cross section for this process, it is given by the amplitude, and the amplitude depends on this phase shift. So the phase shift is essentially the scattering amplitude for this process, but this is more of a side comment. Yeah, so as I mentioned before, there is a special combination that appears in the equations, in the results, and it is this combination of electric and magnetic charges, and it is constrained by duality. So I guess that most of you have heard about the Dirac quantization condition of a system of an electron and a monopole. Dirac discovered that the charges has to be quantized, otherwise there is a singularity. It's not a Dirac string, and to avoid it, we need to impose this quantization condition. So here n is an integer number, and this is the famous Dirac quantization condition. Are people familiar with that, or want me to explain more about the Dirac quantization condition? Okay, so if people are familiar with that, there is a generalization of this condition to the system of dion scattering, and this is called the Dirac-Schwinger-Zwanzinger quantization condition on the charges. Again, it's a generalization of the Dirac quantization condition, and it means that it says that this combination of the charges has to be an integer. Now, it's not a coincidence that this combination appears. This is a combination which is invariant under electromagnetic duality, which is
Actually,
yeah.
Can you go back?
Yes.
So the first condition, okay, that's Dirac. Now the second one, isn't saying that both E and G are individually quantized?
No.
That's one way to achieve this.
Yeah.
But I've got random particles which are interacting. Why would this be satisfied if they have random charges?
Well, that's a condition. Otherwise, there will be singularities in the cross section. So it's a condition.
Condition, okay, but isn't that telling you that nature, in order to be consistent, requires E and G to be individually quantized?
I mentioned in the quantum theory, it means that they have to be individually quantized. That was discovered later on by Uri Kol.
Yeah, but I'm thinking, just looking at these relations, it's probably, okay, we should look into it. But to me, it seems self-evident that they have to be individually quantized.
Yeah, it depends on your assumption. If you assume that I think it's true. Or at least the difference between charges should be quantized. The difference, yes, but it's not strong enough. Yeah, it's not strong enough to constrain individual charges, but differences.
True, it's a difference something, so, yeah, okay.
Yes, yes. So the point that I want to emphasize is that this condition is a result of electromagnetic duality. First of all, this combination is invariant under electromagnetic duality that rotates the electric and magnetic fields into each other, or in other words, it rotates the electric and magnetic charges into each other. And it's essentially a result of this invariance under the SO2 group. Okay, so let me just remind you that the electromagnetic duality is a symmetry of the classical equations of motion of Maxwell's theory. And in the quantum theory, this duality group breaks down to a discrete subgroup. So this is not. I will not be able to go into details about that. Not just for advertisement or kind of the general idea we have in mind. But in the quantum theory, this is broken down to a discrete subgroup. This is the lattice of electric and magnetic charges. And instead of a continuous SO2 group, we have a discrete modular group, SO2Z, that map the coupling constant or the charges into each other in this way. And one element of this group is called S duality. It takes the charge to -1 over itself. This has been an important tool in quantum field theory. The main reason for that is that it maps weak to strong coupling. So that has been a key tool and key results in quantum field theory since the late 70s, I would say.
I have a question about this. Is it that the quantization breaks the symmetry, or is it just spontaneously broken? Like is a Higgs mechanism sort of situation, or is the quantum is the symmetry just not preserved under quantization?
Well, so yeah. So first of all, this is a different theory. It's not Maxwell theory anymore. It's a non-abelian theory. In the non-abelian theory, there is no classical duality of the equations of motion. There is no electromagnetic duality. But it turns out that in the quantum theory, there is a subgroup of this would have been classical duality. So so maybe it's a little bit misleading. In this theory there is no classical duality.
I see.
So this statement is a little bit misleading. Yeah. But that's just So I won't be saying anything related to that. That's too far. But just as an idea of what can we use duality for in the future? Yes, so now the question that I want to pose is, can we realize duality in general relativity? Okay, so that would be, I'd say, the second part of the talk. So far, everything was a review. And now there will be some new results. Can we realize duality? So in a sense, now I want to go backwards. To ask whether there is duality, and using that, try to see whether we can use the duality to constrain the gravitational system, or to find an integrable model. And I won't be able to answer all these questions, but as we will see, we will have some answers to some of these questions. Okay, any questions? So that's the goal for the rest of the talk, to see if we can realize a phenomena akin to electromagnetic duality in gravity. So a brief history of the subject. Actually, people have discovered evidence for dual graviton back in the 80s, but more recently, there were a series of works by a group in Belgium, and the group in Chile, by Claudio Teitelbaum, that then changed his name to Banster. So they studied duality in linearized gravity. In linearized gravity, they showed that the equations of motion are invariant under this operation on the Riemann curvature. But this so that's yes, so that's the epsilon tensor, and it works on it acts on the on two of the indices of the Riemann curvature. This kind of operation is a little bit ad hoc, so it's for that reason it's also not terribly surprising that it doesn't continue to the full theorem. It's not an operation like the odd dual operation of Fishman, which is a little bit more well defined, I would say. Anyway, that's one line of works. There are other books that found some evidence for dual graviton in supergravity theory. Yes. So more recently, we've found a way to generalize some of these results to the full Einstein theory. So it turns out that in order to do that, we need to use the first order formulation of Einstein's theory. In this formulation, okay, let me explain this. Yeah, I guess that most of you have seen this kind of stuff, but if not, I'm happy to explain in more details. But yes, so let's see. This is the Einstein action. It is in the first order formalism. It is given in terms of this quantity. This RAB is called the curvature 2 form. It's the field strength of the spin connection. And these theta's are a set of one forms on spacetime. So they are essentially the field lines contracted with the line with the coordinate. And they are also given in components by the Riemann curvature, projected into the tangent space. So these ABC indices are coordinates on the tangent space. Are people familiar with tangents, with this notation, or yeah, if not, I can try to explain a little more, but if people are familiar. Yes. So this is the first order formulation. This is for people that are not familiar. This is the wedge product. And I also used, I wrote it in a way that is kind of suggestive. I defined here the Hodge duality operation of the curvature 2 form, but this Hodge duality operation acts on the tangent space indices, as opposed to previous attempts to realize duality using this kind of operation, duality on space-time indices. And now we can write the Einstein equations in the Bianchi identity in this language using tangent space formulation and differential forms. So Einstein's equation are given like this: the wet product of R theta and the basis of point forms, and the Bianchi identity are given in this form. So this is a slightly less common form of the equations, and not everybody has seen it, but it's a textbook thing. You can find it in some textbooks. In terms of components and projecting onto space-time indices, this gives the Einstein equations, and this gives the algebraic Bianchi identity. And in this form, it is evident that the equations are invariant under rotation of this curvature 2 form and its dual into each other. Okay, so in this way we can realize duality.
Oh, I have a question. Isn't the duality normally defined in terms of the Hodge operation, the Val tensor, not the Riemann curvature tensor?
Yeah, so I would say that was the mistake that people have made in the past, that what made it difficult to generalize this duality operation beyond the linear order. Well, mistake in quotes, right? It's not the right way to do it. Actually, it was proven that it's not working in this way. Yes, so but one I would say is that this duality operation boils down the linear approximation to this. So I think that was Dominique, right? So Dominique, all the results that you know about perhaps linear in the linear theory about the composition of the Riemann curvature into electric and magnetic pieces follows from that, but that's more general. Is that answer the question, Dominique?
Yeah, I see. So this is more general than starting from the Bell tensor, I guess.
Yes.
I suppose if you consider a matchless theory, they just agree.
What can you repeat?
Vitalist theory.
Oh yeah, that's yeah, without matter, and soon I'll say a few words about coupling to matter. Yes. And there are also different connotations of electric and magnetic components. I'm sure you're probably familiar with the Newman Penrose formalism, and they also define electric and magnetic components. But the key is that in order to realize duality as symmetry, you need to consider this operation on the curvature 2 form, which is also a very natural one because the curvature 2 form is the field strength of the spin connection. So that's very similar to the case in electrodynamics where duality acts on the field strength of the gauge field. Okay, so this is the duality. It is slightly more difficult to see how it works in practice. So let's consider an example. Or before the example, I'll just say that as in field theory, the field strength can be decomposed into its self-dual and anti-self-dual parts, which transform nicely under duality. Okay, so we can decompose any curvature 2 form into self-dual and anti-self-dual parts, and each one of them transform into themselves with a phase under the operation at the H, under this SO2 operation. So let's see an example. The example that I considered is the Kerr tau nut spacetime. So everyone knows what is Kerr. Tau nut is Kerr, which is supplemented by a nut charge, which is the analog of magnetic charge in gravity. So this solution corresponds to a dion, but not just a dion, but a rotating dion. Okay? This is the Kerr as that's the rotation factor. So that's the gravitational analog of a rotating dion. Here I've written it in the Plebanski coordinates. Most people are familiar with the Boyer-Lindquist coordinates, but these coordinates are very nice to work with. It depends on three parameters: the rotation parameter, the Schwarzschild mass, and the nut parameter here is L. And that's a time, I think that should be the same L. And when we compute the curvature 2 form for this background, we found these results for the self-dual and anti-self-dual components of the curvature. It turns out that in this system of coordinates, and you also have to make a smart choice of the basis of field lines, the dependence on the mass parameters is linear, which is quite remarkable because usually in GR, in the solutions in GR, the dependence on the parameters is non-linear, and therefore it's hard to see how duality, the manifestation of duality. But it turns out that in this magical Plebanski coordinates, with some few other smart choices, all the dependence is linear. And from these results and the previous slides, we can now see that under duality, the mass parameters will map into each other.
Uri, you made a comment on the Kerr-tau nut being the gravitomagnetic equivalent of a spinning diamond.
Right.
So if you just look at tau nut,
Yes.
no spin.
Yeah.
So in that case, how do we understand this as a dion? What is the gravitomagnetic piece doing? Is it like
It's an analog of a dion.
So is it
rotating?
So it's a rod singularity, which is the
Yes.
nut,
Yeah, it's a Meissner string.
and it has angular momentum.
No. Well, it has. Actually, it does because. Okay, so in the charge monopole system, there is automatically angular momentum just because of the interaction, the interaction with the constant magnetic field. So there is angular momentum. Yes, actually. Yes, yeah, that's a good question. So yeah, I'm happy to talk more about the monopole system and questions. Yes. But it's an intrinsic. It's not orbital environmental.
So the rod is just spinning on
Yeah. I guess you can think about it this way. But
Is there a,
yeah.
is there a geometrical interpretation of the duality, and is there a way we can understand it?
So it's a symmetry of the equations of motions.
Mhm.
It maps solutions into each other, and what we see here. So if we combine this result with the previous results on duality, what it means is that it maps the mass parameters into each other. It rotates them into each other. So in fact, we can map Schwarzschild or Kerr into Kerr-Tau-Nat to add this magnetic factor. Yeah, so of course, everything I showed so far is in the framework of.
And we can tell that because the SO2 is fundamentally electromagnetic. I mean, it's bringing in the electromagnetic.
Well, everything is gravity.
Right.
So this is the analog of the statement is that this SO2 is a symmetry of the equations of motion. That's a statement, and it maps solutions into each other. In the same way that in Maxwell's theory, electromagnetic duality maps solutions, in particular, it maps the Coulomb charge into a diamond. So that's the statement. And there is the question that is still unsolved. So this is the equations of motion in the vacuum. Now, when we say that Schwarzschild is a vacuum solution, we ignore the source, right? So this is a long-standing problem of how to source this metric, and these results do not address it because everything is in the form of vacuum equations. But otherwise, that's the statement.
Uri,
Yeah.
Okay.
maybe just to second on Peter's question, is there any like conformal symmetry playing a role here? I mean, you showed us this SO4,2 group acting on the wave equation. Is this part of that conformal structure that's also present in electromagnetism, or is
Which
it something
conformal?
else?
Which
This SO4,2 structure you showed, I guess that's for the wave equation, but I was wondering if it's. I mean, this is in the hydrogen atom. This is the symmetry of the wave equation, right? Because
right.
you can map the dione system to hydrogen atom. So is that part of the conformal? Yeah, maybe this is too convoluted, but
Yeah, well, yeah, I guess.
Is there anything conformal here?
Yeah, it's a good question. I don't know, but the way I presented it is suggestive that there is a connection between the symmetries of the atom and duality. But it's yeah. Well, you will talk next week about the conformal symmetry of the gravitational system. So I think it is related, but yeah, I don't have something smart to say about it. Alfredo.
I see.
I have a quick question. Is the self-dual and the anti-self-dual parts of the Taub-Knot metric under this definition of duality the same as if you had used the vowel tensor?
No. Why tensor you mean with space-time indices, right?
Yeah.
No, they're not. That's a key actually. So yeah. So when you compute the Y tensor or the Riemann tensor with space-time indices, you will not see this duality property. It will not transform nicely out of duality.
So just on this, in electromagnetism, the field strength that you're using is the Maxwell field strength, which is coming from a linear theory. So if you were to project all that onto some basis one forms, or onto some
Maxwell theory?
In Maxwell theory, you probably get the same sort of structure.
Yeah, but in Maxwell theory, it's kind of trivial.
It's because
it's on flat space anyway.
Right. So here the thing is that because you have curved space, you can't do this in space-time coordinates, but you can do this in.
Yeah, in a way, I like to think about it as a theory of a curvature two form on a flat tangent space.
Okay.
So, and then you can map the duality rotations are in the tangent space. So you have a space-time solution. You elevate, you map it to the tangent space, you dualize, you do the duality, and then you can map again to a space-time.
Okay.
That's the way I think about it. So yeah, in the last few minutes, let me also say a few words about coupling to metal. So as we see, like someone mentioned before, coupling to metal will break this duality because it sources Einstein's equation, but it doesn't source the Bianchi identity. And so how can we restore duality? So that brings me to a topic that
is this true also in Maxwell?
so in Maxwell you can introduce magnetic currents, right? In Maxwell, back to Maxwell. In Maxwell, you can solve the Maxwell equation and you can introduce.
Oh, I didn't see you put the change in there as well. Okay, okay.
Magnetic charges, and in the presence of currents, duality will rotate the electric and magnetic fields into each other, but also the currents. So everything is good. But in Einstein's theory, only Riemannian surfaces, this is zero by definition. So what do we do to restore duality? We need to source the Bianchi identity again, and we have heard from Ellen a few weeks ago about how to do that with the Einstein-Kaplan theory. So in fact, that's one of the reasons that we set up this talk because of this connection.
Actually, can you explain that a bit more?
Yeah, I'm going to explain.
Yeah, because if you can do it in Maxwell, what's stopping you here?
Einstein theory is by definition a theory of Riemannian manifolds.
Yeah.
Riemannian manifolds by definition obey the Bianchi identity. So you cannot source this side of the equation in Einstein's gravity.
If I may, by very poor analogy, I will say that. So there in the Maxwell theory, he has introduced a magnetic monopole current, for example,
Yeah.
a magnetic current.
Yeah.
Here it's like saying that the equivalent stuff is you have Christoffel symbols but zero spin connections. The spin connection will give you non-zero torsion or zero torsion in Einstein's theory. So you've already fixed torsion to be zero, which is like setting in the Maxwell theory J tilde to be zero. So now he's relaxing the torsion freeness.
Yeah.
And then you will get
Right,
also this
okay.
ability to turn them into each other.
Yeah, okay. That sort of makes sense, yes.
Yeah. In Einstein theory, it's simply, I mean, this is not zero and this is always zero. So there is no way that you can make it
That Bianchi identity or zero torsion equivalent to saying there are no magnetic terms.
Yes, that's the gravitational analog.
Analog, okay,
Yes.
okay,
Yes.
good.
So you need, in other words, you need to enlarge your phase space of the theory to allow for violations of this, and
Like it will be equal to zero.
Right, exactly.
Yeah.
Okay,
Exactly.
okay, good.
and you do, and the way to do that is in the Einstein-Kaplan theory. So there is torsion. Torsion is the anti-symmetric part of the connection.
Sorry, Ramesh, you said that's the gravitational equivalent of the no monopole structure?
It will be equal to zero. We hardwire it to Maxwell.
Yeah.
Right,
But if you put, duons in Maxwell, you'll have to give up div b equal to zero. You put magnetic charges.
Well, at least monopole field, not
Monopole,
yeah, monopole field, not any magnetic field.
there are gravitational monopole, I mean, I don't understand, why,
No, the
There's no-
gravitational monopole is like the electric charge.
Yeah.
right,
But there is no equivalent of a magnetic monopole
right,
in Einstein's gravity. But
So I would say when you say there is no equivalent, so people know about tau naught. Tau naught is the analog. The problem with tau naught is that it doesn't obey this because there are some violations of the singularity, and there is nothing to balance them on this side. So that's a way to describe the problem with tau naught.
Yeah, I think so. So it's basically like say, when we describe Schwarzschild, we're not looking at the center.
yeah,
So here we're not looking at the line
No,
singularity.
but it's more than that. Because in Schwarzschild we can at least balance the singularity.
Right.
For tau naught, which is the gravitational dion, we don't know how to balance it. So we don't know what is the meaning of the singularity that we have. So yeah. And that's part of the motivation for this, to understand how to solve our math. But anyway, let me try to wrap up. So this is the torsion. There's also something that is called a contortion tensor. It's the addition to the connection, in addition to the Christoffel symbols. It's a function of the torsion tensor.
Is the contortion tensor always anti-symmetric? In
Yeah,
the bottom blue?
The contortion, I think, yeah, I think it's anti-symmetric under the first two indices, if I'm not mistaken. Yeah, it has some properties. Yes. And yeah, so on this Riemann-Cartan manifold, we can the curvature tensor. Also, I would note the generalized curvature tensor of this manifold by theta r theta. It decomposes into its Riemannian piece and contribution due to torsion or contortion. Okay, so again, the details are not important, just the fact that they decompose. And now the Bianchi identity is solved by the torsion. So here, instead of having 0, because in Einstein's theory, we have something which is proportional to the torsion. So this is called the torsion two form. It's a two form that depends on the torsion tensor. Anyway, I need to wrap up. So just to mention an example. Still, before the example, so now we can consider this theory, and we can look on what duality is, the action of duality on the action, or how the action transforms under duality. And it turns out that under duality, the action picks up a boundary term, and this boundary term is a divergence of some current. So we can identify this as the gravitational duality current. It's a function of the tensor, and this is the analog of the duality current in Maxwell's theory. So in Maxwell's theory, the equations of motion are invariant under duality, but the Lagrangian, in fact, is not invariant on the nose. It picks up a boundary term, a total derivative terms, which current is known as the duality current. So this duality current is related to the helicity current of gravitational of electromagnetic waves, for example, but it's more general. So anyway, that's in Maxwell's theory, and we found the analog of the duality current in gravity. And that's just a quick example of a theory which is known as NS gravity. It appears in all supergravity theories. In addition to the graviton, a dilaton, and Karl-Brauer field. The Karl-Brauer field is essentially an axion. It can be dualized to an axion. And this theory can be embedded into a Riemann-Cartan manifold, into a contortion tensor. So it is invariant under duality. So we can think about it as a Riemannian manifold coupled to some other fields, or we can think about it as a Riemann-Cartan manifold with some torsion.
Wow, and they're exactly the same. These two are exactly.
Yes, you can. Yes, that's this is not. Well, it's not how many years that these matter fields can be embedded as torsion components. Anyway, I'm running out of time, so I'll try to wrap up. In the heterotic string, in the linear approximation, we found that duality of the curvature tensor implements few different dualities at the same time. Duality of the metric, the Riemannian metric, axial dilaton duality, and electromagnetic duality. So this is evident from the structure of the curvature tensor in the heterotic string, which includes this field. So this duality of the curvature tensor implements at the same time all these types of duality.
So one last one,
Yeah,
sorry.
yeah.
When you say low energy action, this is in 4 dimensions, right?
Yes.
Wow.
Yeah, I'm a little, yeah, I can talk, maybe I can talk more.
Okay,
But just an example, so maybe I should not spend And let me just end by saying that this duality symmetry is a fixed point. Fixed points of this the duality is where the background is completely self-dual or anti-self-dual. In a situation where the background is self-dual, meaning that the anti-self-dual components of the geometry vanishes, the duality operation will keep the space-time is self-dual, so it will not map the self-dual and anti-self-dual separately. This is why it's called fixed point. If we're at this point, we stay at this point under the duality operation, and it turns out that these models are integrable. Okay, that was known before, not yeah, but that was not before, even though the duality operation itself was not known. But I can explain why exactly, and that will be the subject of and further we'll talk about it and perhaps on other things. So let me just end by some future directions. So one thing that I already mentioned is how to solve Carnax. So this is a long-standing problem, and that's one of the reasons that we wanted to study duality in the presence of matter, because the hope is that we develop the tools to now be able to map the Schwarzschild source into the Carnax source. But there are more, I suppose there's some more general directions. So if we understand now the classical duality in gravity, is the gravitational quantum version of S duality? And can it hint about quantum gravity? So I wrote quantum gravity just to trigger mine, but I think that's probably too much to work for. But I think that maybe S duality will be there in gravitational theory and will teach us something. Can we use duality to constrain the black hole spectrum, like it constrains the spectrum of the diamond system? And then further question is whether we can use non-perturbative methods in like has been done in supersymmetric field theories. And yeah, I think I'll end here. Thank you.
Any questions?
I have a question. This seems kind of remarkable that you know, the connection between this and electromagnetism is very clear. Do you know why people originally constructed these dualities with the Weyl tensor first instead of using the curvature form?
Yeah, I don't have a good answer for that. Yeah, I mean, yeah, I don't have a good answer. This is actually pretty simple. This form of equations, it appears in some textbooks. It's less common maybe, but yeah, I don't have a good, yeah, I don't know why people. It took some time, I guess.
I have a question on
Yes.
the low energy effective theory. So we know from
Thing.
so the solutions to this exact equations are this like for spinning charged black holes
Yeah, right.
under electromagnetism, dilaton and axion. Yeah, this is called this Curson metric, right?
Right.
And
Well, this is
we know it's not type D, but we
Right.
know it admits a Carter constant. We also know that the Tchaikovsky equation, I think, is also separable. And it's not just self-dual and not at this self-dual or anti-self-dual points. So it's more general than that.
Right.
So is there any way to understand when you go off of the self-dual points, why you're getting these symmetries as in the Hamilton-Jacobi equations? Yeah, so it's more general than that.
I don't have an answer for the question. We are thinking, I mean, people are thinking about
Right.
it. Yes.
Yeah, also, just on that point, we like just the existence of these Killing-Yarrow tensors,
Yes.
that does not directly lead you to separation of these wave equations.
I think it does.
It does.
Yeah, but it's not clear why the other in the first place.
Why? Okay, I see.
By the killing with the other. Yes. Yeah.
As another question, in terms of like measurement, it seems like if you formulate the duality in this way, then it kind of gives you an obvious place where to look if you're looking for the existence of torsion or not, which is in the violation of the Bianchi identity. Do you know like do you have any idea of like what sort of I guess physical
Yeah.
process would
Yeah, that's one of my missions, to convince people that tau nut is real. We are still not there, as you see, because we didn't address the problem, so it's still not there. But yes, if we understand how to source tau nut, essentially we can argue that it's physical. It can have a signal in the two-body problem, in gravitational waves, but it can also have a signal if we observe the motion of stars around it.
Precession.
Not just possession, but if this is real, if tau nut is real, it means that, let's say, a black hole, let's say the supermassive black hole at the center of the galaxy, if it has this gravitational magnetic charge, it will have an effect on stars that orbit it, right? It will have an effect similar to the effect of a field of a magnetic monopole. It will be a gravitational magnetic monopole, and we can observe it.
Yeah.
So if there are astrophysicists in the crowd, I urge you to try to look for a magnetic monopole.
So actually on that, should the star also be a dion, or is it enough if it's a normal object?
It could be in principle, but yeah.
But there would be an effect even if only the SMBA.
Oh yeah, yes.
Oh, there'll be an effect even
Yes.
if only the black hole has got this.
Yes,
magnetic.
yes.
Okay.
It will be a gravitational magnetic monopole field.
That will give an effect. Okay.
Yes. So yeah, Dominic, I'm trying to convince people to try to look.
One thing I will just mention in this thing is that there's work done by Chandrachud Chakraborty on there's an author Chandrachud Chakraborty. I met him when I was a PhD student. He was a postdoc. So you can do actually, if you look at stars orbiting this supermassive black hole which has this tau nut charge, then there'll be a spin-spin coupling. If the star is also spinning.
Yes.
And in particular, if the charge is a pulsar, then it will undergo spin precession, which will be linked to this tau nut charge.
Yeah,
And so you will see the rate of pulses on Earth, which will be different. And so
I think there will be different effects associated with it. But I think the simplest one is just the monopole.
Exactly.
The monopole field.
Yeah.
That's the most.
So there are some effects.
Okay, very good.
Yes.
So I'm sorry to be dense, but okay, so there's a gravitational analog of magnetism, right? In the spinning satellite test that they,
Right.
right? So, but what I'm still missing is what's the analog of a monopole, of the no monopole condition, or what?
I think the one that you're thinking of is exactly what a tau nut charge will do. So this is the gravitomagnetic charge, the frame dragging.
Yeah.
And now this is going beyond that. I don't really understand still whether if you have a nut charge and you source it, are you saying that there will be non-zero torsion?
Well,
I think he's asking what. Sorry.
Yeah, so just to source tau nut with torsion. Yes, that's one way to say.
So sorry, with the second equation not equal to zero.
Yeah, with torsion.
That will
So
require-
one way to source it is by introducing torsion.
Right. So I guess that's to get that thing without. So if you don't have a spinning black hole,
Right.
if you have a static, if you have a gravitomagnetic monopole, you will
Yes.
still put out this field that will cause this precession that you're thinking of, the gyroscopes. And we don't understand how to satisfy the Einstein equations with this gravitomagnetic monopole. So Uri's work is suggesting that we actually need some torsion to then satisfy the field equations properly.
Yeah.
And that is what would give you this without even spinning black holes.
I see.
Right.
Sorry, I'd like to add an additional comment. So there was the statement about the no monopole, I guess, identity. So in electromagnetism, the no monopole condition is the Bianchi identity. So I think the equivalent in this formulation of duality in GR is also the Bianchi identities.
Yes.
So in the sense that for electromagnetism, in order to have that full duality, realize you have to relax the Bianchi identities. I think Uri is suggesting you have to do the same thing here in GR.
Right. But in GR it's more tricky because in Maxwell you can just introduce a magnetic current, and here in Einstein theory you cannot do it by definition. So
yeah.
But anyway, that's it.
Yeah, thanks everyone for joining. Let's and we'll see you all next week for the continuation of this series.
Helen, Prashant, I have a suggestion.
Okay.
Peter also. Let us encourage local people to actually come here. discussion through,
Yeah.
it never works. It's too much cross-talking, and you don't know when the question is finished, and you don't hear properly.
It's so early in the morning.
It's early in the morning, yeah, but they can come if they're interested, yeah. Yeah, Dominic should have been here instead of,
I can add a note. and
Yeah, I don't know.
know.
You agree with
Yeah,
this?
sorry.
I don't know.
Yeah, Dominic should have been here. It's
Yeah,
so-
I will be
discussion
here
more
next
better
time.
than
I agree.
Yeah, I think.
Yeah, I think.
Interesting.
Oh,
Yeah. This is a dimension I never thought about.
Yeah.
Or heard about.